Welcome friends, welcome to this GATE Fast Track course, and in GATE Fast Track course we are studying strength of materials, okay, and in strength of materials today we'll be seeing columns and combined stress. So welcome to all the participants who are watching this lecture live, and also to the participants who are attending recorded. We'll start in few seconds. Today is lecture number 8. Yes. So previously we have covered many important topics. Okay. In the previous classes we have completed bending stress, shear stress, torsion, Mohr circle for stress and strain, right? And today we'll be seeing columns actually. In columns we'll be covering what? The most important topic, that is buckling load. Yes. And then we'll be seeing combined stresses. In combined stresses we'll be seeing the combined stresses in a column and also the combined stresses due to combined torsion and bending moment. Okay. So let us start the class. Okay, we'll start in few seconds. Just wait for some time. We'll start the class with buckling load. We'll start with what? Buckling load. Okay. So let us start with what? Buckling load. Okay. We will start with what? Buckling load. Okay. So in columns, the most important topic is Euler's buckling load, and we will be seeing this. Right. Now columns are what? Columns are compression members, right? What are columns? Columns are compression members. That means what? They are subjected to what? Axial compression. Compression members means what? They are subjected to axial compression. So like this, they are subjected to what? Axial compression. Okay. So since they are subjected to axial compression, there is possibility of what? Buckling. Right? There is possibility of what? Buckling. And the load which is responsible for buckling is known as what? Your buckling load or critical load. This is known as what? The buckling load, okay, or critical load, or what? Critical load, right? So, and this is also what? The Euler's buckling load is given by Euler's. So it is also known as what? Euler's buckling load. Yes, the load responsible for buckling of this column is known as what? Euler's buckling load. Now what is the expression for Euler's buckling load? The expression for Euler's buckling load is pi square. It's what? Pi square. Then E. E is modulus of elasticity. Then I minimum divided by what? L effective square. Divided by what? L effective square. So this is the expression for finding what? Your Euler's buckling load. It is the expression for finding what? The buckling load or Euler's buckling load. Now any cross section, if you see any cross section, let the cross section be, rectangular or circular. Yes, suppose it is rectangular or circular, right? Or any other like I section, T section. I'm not drawing them. So they will have what? They will have two axes, right? Yes, they will have two axes. In circle, the two axes are actually same, okay? But in rectangle, they are different, right? And therefore, if I am seeing a rectangular cross section, right? Then it will have IXX and IYY, and both will be what? different, right? And we have to take what? The minimum of them. I have to take what? The minimum of them in the buckling load calculation, right? In the buckling load calculation. So for a rectangle, I can say that Ixx will be what? Ixx will be BD cube by 12. Yes. And Iyy will be what? It will be DB cube by 12. Right? Yes. BD cube by 12 and what? DB cube by 12. Right? And this is what? For a circle, actually both are same, right? So in circle, I can say that your Ixx will be equal to Iyy will be equal to what? I minimum and will be equal to what? Pi by 64 d to the power 4. Pi by 64 d to the power 4. Yes, have to remember these things, right? This is for a rectangle and this is for a circle. Very nice, no problem. Now, in this equation, we saw I minimum, E is modulus of elasticity, pi is pi only. What is this effective length? This effective length, it is equal to the effective length factor K into the unsupported length. Okay, into the unsupported length. So what is this effective length factor and on what things it depends, right? So this is your effective length factor. What is this? This is effective length factor and it depends on the boundary condition. Okay, it depends on the boundary or end support conditions. It depends on what? Boundary or end support conditions. Very nice. So we'll see different support conditions and then from there we will try to understand how to find out this K. But before going into that, let us see what type of support exists. Okay. So we'll have a support like this. This is what? This is the fixed support. When it is indicated like this, this is what? Fixed end or fixed support. In fixed, I can say nothing is allowed. That means what? In fixed, I can say that translation is not allowed. Translation, or I call this as what? Lateral movement. Translation, or I call this as what? Lateral movement. So what is translation? Suppose I am talking about this point. Suppose you see this point. Translation means it is not moving in this direction. This is not moving. Or you can say translation means moving. Okay? This is what translation. Or this is also translation, right? This is also translation. Even this is also translation. Right? Even this is also translation. You can say vertical translation, right? So if there is lateral movement, this is known as what? Your translation. Right? So in fixed end, translation is not allowed. Yes, no movement is allowed. And rotation is also not allowed. The other kind of movement which can happen is rotation. Rotation is not allowed. Rotation is also not allowed. Okay. So whenever translation is not allowed, this is also indirectly told as what? Held in position. Indirectly known as what? Held in position. Held in position means what? It is not able to change the position. So held in position. Yes. So when I am telling that, translation is not allowed. So translation not allowed means wherever is the initial position, it will remain in that position, right? So translation not allowed means if this point is here, this point will be here only. It cannot move, so it will be here only. So means what? The position is fixed, or I can say what? Held in position. I will tell this as what? Held in position. Very good. Held in position. Now rotation is not allowed. This is indirectly known as what? you're held in direction. It is indirectly told as what? Held in direction. Held in direction. Because rotation not allowed means what? If rotation was allowed, suppose rotation is allowed, that means what? If rotating means what? Direction is changing, na? If it is rotating, this means what? Direction is changing, na? So if I am telling that rotation is not allowed, that means what? This direction is fixed. No rotation means what? Direction is fixed, or I can say held in direction. So these are, we can say, alternative way to write what? That translation not allowed is held in position, and rotation not allowed is held in direction. Is what? Held in direction. Right? This is fixed end. If we have pinned or hinged end, if we have pinned or hinged, it is indicated like this. Pinned or hinged end, you see, it is indicated in this manner. Okay, this is what? Pinned or hinged. So in pinned or hinged, the translation is not allowed. Translation, or I can say lateral movement. Translation, or I can say lateral movement, or I can say lateral movement. So in this pinned, translation and lateral movement is not allowed. Yes, but rotation is allowed here. So rotation is allowed. It can rotate, but it cannot translate at this point or support. So rotation is allowed. So when I say that translation lateral movement not allowed, it is indirectly what? Held in position. But I cannot say it is held in direction. Why? I cannot say it is held in direction. Why? Because rotation is allowed. So if rotation is allowed, that means what? That means direction can change. So it is not held in direction. So this is pinned and this is what? Your fixed. Okay. And last one is free. Free means what? Means both are allowed. So easy. Let us go to, different cases. Okay. The first type of, we can say, column will be what? That both ends are fixed. Both ends are fixed. Like this. Both ends are fixed. Okay, both ends are fixed. So, but in the examination, they don't write as simple as that, both ends are fixed. They don't write like this. They don't write both ends are fixed. They don't write both ends are fixed. They write in different language. How they will write? They can write in multiple languages. They can write like this, you see. One option is held in direction. Held in direction. Held, don't remember, understand. Held in direction and position at both ends. Held in direction and position at both ends. You can see that at the both ends, what is happening? That rotation is not allowed and translation is not allowed. That means what? It is held in the position and direction at both ends. Right? It can be also written like this, that translation and rotation, translation, or they can write down lateral movement also. In place of translation, they can write down what? Lateral movement. So translation and lateral movement and what? Rotation. Okay, rotation, both, na? This and this. Either they can write what? Not allowed. Or they can write what? Not allowed means what? They can write down restrained. Or they can write down what? they can write down your restricted, right? This kind of language they can use, restricted at both ends. So at both ends you can see your translation and rotation are what? Are restricted or not allowed, or I can say restrained. Yes, very easy, very easy. Yes, yes, very easy. So in this case, the K is half, or I can say 0.5. Okay, K is what? Half or 0.5. Okay. Next is your one end is fixed, one end is hinged. Okay. So one end is fixed, suppose this is fixed. Okay. And other one is hinged. It can be reverse also. Top one is hinged and this is reverse also. Just I have drawn here like this. So this is what? Pinned. So when it is pinned, I can say that here you can see that here at this end rotation is allowed but translation is not allowed, and here translation is not allowed, rotation is not allowed, right? So what is the language we can use? The language we can use, multiple languages we can use. One is that held in position at both ends, held in position at both ends, right? Held in position at both ends. How? In both ends, you see translation is not allowed. Translation is not allowed means what? Held in position. Okay. But held in direction. But what? Held in direction at one end only. Yes. Held in direction in one end only. You can see that it is held in direction at one end only. How? Because rotation is restricted only at one end. Other end it is allowed. Yes. That means it is held in direction at one end only. What else language it can use? Other languages can be translation or lateral movement. Translation and lateral movement. Restricted or restrained or not allowed. I'm not writing everything. So restricted at both ends. You can see that translation is restricted at both ends. Yes. And I can say rotation. But what? Rotation. But what? Sorry. But rotation is restricted at one end only. Na? We can use restricted or we can use restrained or not allowed. In many languages we can use restrained. But you see, rotation is restrained at one end only. Right? Translation is restricted at both ends. Yes, translation is restricted at both ends, but rotation is restrained at one end only. That means other end it is allowed, right? So this kind of language they will use, and you should be thorough with this kind of language. It's not that always they will write, fixed and pinned. Okay, they write very good, but many times they don't write. Here K is 1 by root 2, or I can say this amounts to 0.707. Very good. Nice. Next one is both ends are pinned. Next one is what? Both ends are pinned like this. This end is pinned. Yes. This end is pinned. And then this end is pinned. Yes. So both ends are pinned here. Right? This is also pinned or hinged. Okay. This is also pinned or hinged. So if it is pinned at both ends, that means what? That means you see rotation will be allowed at both the ends, right? Rotation will be allowed at both the ends, but translation won't be allowed at any end. So we can use the language, what language we can use? Held in position at both ends. That's it, right? Yes, held in position at both ends, right? If it is held in position in both ends, nothing mentioned about direction, that means it's not held in direction, right? Indirectly we can say, right? Yes. Or we can say held in position only at both ends, right? Means what? In position only it is, we can say held. Or we can write down only translation or lateral movement is restrained at both ends, right? Yes, only translation is restrained at both ends. If translation is restrained at both ends, that means what? It's written only, that means what? Rotation is allowed at both ends indirectly, right? So such kind of language they can use. And here the K value is what? The K value is 1. Now last one you see, one end is free, the other one is fixed. Something like this. So here it is fixed and here it is free. Okay. So free means both translation and rotation is allowed, right? So here rotation is allowed, translation is allowed. Here translation is not allowed, rotation is not allowed. So I can say, what language I can use? I can use that held in position. What language I can use? I can use held in position, yes, and direction. Held in position and direction at one end only. Okay, held in position and direction in one end only. Yes, in one end only you can see that it is held in position and direction. Means what? In this end both rotation and translation is allowed. So when they are writing at one end only, what is the meaning? At the other end it is not held in position, right? Indirect meaning is this. Or other language they can use is what? Other language they can use is that translation and rotation. Translation and rotation. Translation and rotation restricted at one end only. Okay, very good. So in this case, the K is what? 2. In this case, the K is 2. So let us summarize them. Okay, let us summarize them. So buckling load is what? Buckling load is, we have seen, buckling load is equal to pi square E I minimum, or I can write down I, that I is I minimum only, I divided by L effective square, right? L effective square. Now see, if both ends are fixed, if both ends are fixed, then L effective is equal to what? L effective is equal to L by 2, na? It is L by 2. So equation will change to what? The equation will change to, you see, means change means just take a new form. The buckling load will be equal to, it will be pi square EI divided by, in place of L effective I will put L by 2. So L by 2 whole square. So it will be L square by 4. So both 4 will go up and I will get the expression what? I'll get the expression 4 pi square EI by L square. Yes, this expression we will get. Why? because in this case, nice. Next is right. Next is if I say both ends pinned. If both ends were pinned, then L effective is equal to L only, na? So in this case, can I say the buckling load expression will be what? The buckling load expression will be simply pi square EI by L square. Because what happens? In this case, the L effective is equal to L. Easy, right? Next is that if I say one end fixed, one end pinned, right? Yes. If I say one end fixed, one end pinned. In this case, what happened? In this case, your L effective is equal to L by root 2, right? So, what I will do? I'll put here expression PCR is equal to, okay, pi square EI divided by L effective square, so L square by root 2 square, so L square by 2, and 2 will go up. So what I will get? I will get 2 pi square EI by L square, because it becomes L square by 2 actually. And then last one, see all this directly asked in the examination, expression in match the following and many things. One and free, other fixed. In this case, your L is, K is what? 2 actually, 2L. So in this case, what will happen? Your buckling load becomes equal to what? It will become equal to pi square EI divided by, here L effective is 2L. So 2L square is 4L square. So the 4L square, because here the L effective is what? Your L effective is 2L. Hope this entire thing is clear, right? Hope this entire thing is clear. And they can ask you expressions, they can ask you questions. Whatever they ask, we are ready for this, right? Whatever they ask, we are ready for this. So let us solve some questions. Then we'll come back to some other terms also. But let us first solve some questions. Okay. First I will write down the options. Then we'll write down the questions. Okay. Question is, when translation is restricted at both ends, when translation is restricted at both ends and rotation and only one end is held in direction, only one end is held in direction, effective length factor is. What is the right answer to this? What is the right answer to this? When translation is restricted at both ends and only one end is held in direction. Okay. So you see, always they're not going to ask you very simple that this is fixed, this is no. They're going to ask you in complicated language like this. But if you have understood the things, then you can easily solve this complicated language also, right? So what is this? You see, just draw the column. Then translation, rotation. So you see what is written? Translation is restricted at both the ends. So restricted, restricted. Then what is written? Only one end is held in direction. So if only one end is held in direction means what? Only one end is held in direction means one end is restricted for rotation. So one is restricted for rotation, that indirectly means what? Other one is allowed. So that means what? It is the case of what? One end is pinned, this is pinned, and this is what? Fixed. So in this case, the K is what? The K is 1 by root 2. Yes. So this can be a 1 mark question in the gate, and they are not going to write you that, they are not going to write you that this is one end pinned and one end fixed. That will become very easy. If they ask you, very good, no problem. But that will be very easy. So therefore they will use such language, and it is expected to understand this language. Don't try to remember the language, try to understand. Okay, don't try to remember, otherwise there are so many things to remember. Yes, try to understand the language. If you understood language, you can easily solve this kind of questions. Okay, let us solve another question. Let us solve another question. Let me write down the question. Suppose we have a square column, square cross section, no, not square, rectangular cross section column like this. So rectangular cross section column, and the dimensions are 100 and 120. Dimensions are 100 and 120 mm. Okay, mm. Okay. Then it is given that your E is 2 into 10 to the power 5 MPa. It is given. So E will be given, don't worry. Yes. And your effective length directly is given 3 meter. See, they might give you the effective length, or they might give you what? The unsupported length and the support condition. But here suppose at least effective length is given. So here buckling load is asked. So you have to find out buckling load in kilonewton. That is very easy, right? If you want to find a buckling load, so formula is what? It is pi square EI by L effective square. So here what happens, you see, here we have two axes, right? Here we have two axes. One is this axis and one is this axis. So if I find out the I about YY axis, it will be what? dB cube by 12. So 120 into 100 cube by 12. And if you want to find out about IXX will be what? BD cube by 12, right? It will be what? BD cube by 12. So 100 into 1, sorry. You can say IXX is equal to 100 into 120 cube by 12. Obviously you can see by without calculating also you can see that this will be minimum, right? Yes, without calculating also you can see that this will be minimum. This is 120 into 100 cube, and this is what? 100 into 120, so it will be minimum. So I'll take the minimum for the I. Now what I will do, I'll put everything in Newton mm. So it is pi square 2 into power 5. Then I, how much I will get? This is 120 into 100 cube by 12. And then L effective square. L effective is 3 meters, so I'll put 3000 mm square. So if I see the units, what will happen? You see, this E is in Newton per mm square. I will be in mm to the power 4, right? This is mm to the power 4. And then you see, then your this is in mm square. So what will happen? You see, this get cancelled, this becomes square, and then again this get cancelled. I get in Newton. If I want to get in kilonewton, I'll divide by 10 to the power 3. So this is the way we can easily find out what? The buckling load of any column. Okay. By this we can easily find out what? The buckling load of any column. So how much you are getting? Please tell. Someone is different value you are getting. Let me calculate. Let me calculate. 2 into 10 to the power 5 into 120 into 100 cube into pi square. Further divide by 2, further divide by 3000. Further divide by 10 to the power 3. It's getting 2193.25. Yes, 2193.25 kilonewton. So if they ask you for any cross section, right, just find out the I minimum, right? I minimum, and then rest is simple calculation. You should be knowing how to find out L effective, right? So that is KL. I have already told K and all, right? Easy. Now, if you see a circular section, okay, if you see a circular section, here, your I minimum is what? I minimum is equal to your pi by 64 d to the power 4, right? Because here both is same. Now, I want to introduce one concept known as what? Your radius of gyration. What is your radius of gyration? You see, what was the buckling load? The buckling load was pi square E, I can say I minimum by L effective square. Yes, I minimum by L effective square. This is what? This is the buckling load. This is what? Buckling load. If I am interested in finding the buckling stress, and that I will call as FCC, buckling stress, that I call as FCC. So what is the buckling stress? It will be buckling load divided by area, right? Simple. So buckling load is already pi square EI. So then this is L effective square. Then just divide by what? Area, right? Now this, and see, this is what? I minimum, right? This is I minimum, right? So you see this term, you're getting this term, right? I minimum by A. This term is actually known as what? R minimum square. This term is known as what? R minimum square. And I get R minimum is equal to what? Root under I minimum by A. And this term is known as what? Radius of gyration. And also is known as the minimum radius of gyration in this case. It is the minimum one, right? I can say minimum radius of gyration. Okay. So if you see R, we will have a RXX also, na? RXX will be what? IXX by A. And what will be RYY? RYY will be equal to IYY by A. Now, out of these two, whichever is the minimum, for that corresponding will get the R minimum, right? Yes or no? Very simple, right? If this is minimum, then I'll get this as minimum because A is same, right? Yes. So minimum of these two is known as what? your R minimum. Now is what? R minimum. So I can say R minimum is I minimum divided by square root of A. Very easy, right? So if I am interested in finding the radius of gyration for this circular section, then what is the radius of gyration? Yes, very easy actually. If this is D, then the R minimum will be equal to what? It will be square root of I minimum divided by area, right? So what is I minimum here? It is pi by 64 d to the power 4. And what is area of a circle? Pi by 4 into d square. So see, pi get cancelled. This d square get cancelled. I get a d square here. And this get cancelled. I get a what? 16. So if I take the square root of this, so d square will become d and 16 become 4. So R minimum for a circular cross section is what? Diameter divided by 4. So they can ask you an objective question, right? They can ask you an objective question. They will give the diameter of a circle and they will simply ask what? Find out the minimum radius of gyration. Nothing but d by 4. If you know this conclusion, you can solve the question in seconds only. I am not solving any question for this because it is too straightforward, right? It is too straightforward that they give you suppose 500 and they're asking you R minimum 500 by 4, 400, 400. 1 mark question they can ask. Or they can ask, you know, in MSQ also. So this is what for a circular section R minimum. Okay, circular section R minimum you should know. Next is for a if I say plate. So for a plate is normally what? Plate normally is having rectangular cross section, right? If you see a plate, what is plate? Plate will have a rectangular cross section, right? But in plate what happens? You see, this is a plate. I'll draw a plate. This is a plate. Okay. This is a plate. Yes. So in plate what happens? You see, this is the width of the plate, this is the thickness of the plate, and this is the length of the plate, suppose. So if you see, the cross section area is this one, right? So cross section area is this one, which is a rectangle actually, but in this rectangle this is width of the plate and thickness is less. So if I find out Ixx, it will be what? It will be bt cube by 12. Obviously bd cube by 12 or bt cube by 12. What will be Iyy? Iyy will be equal to tb cube by 12, right? tb cube by 12. Yes, or db cube by 12. Now see, out of these two, thickness obviously will be less than width, na? Thickness obviously will be less than width for a plate. Yes. So obviously this will become what? The I minimum. This will become what? The I minimum, right? And I can say that what will be R minimum then? The R minimum will be equal to I minimum, which is bt cube by 12 divided by what? Area of cross section area is what? B into T. So what will happen? You see, B get cancelled. This get T square. So R minimum of a plate is simply what? T by root 12. Remember this. Thickness by root 12. They can directly ask you in the examination. It's nothing but what? T by root 12. Directly they can ask you in the examination. They will give you thickness and they will ask you the minimum radius of gyration for a plate. Simply take thickness. I am not solving a question. Very straightforward thing. Okay. I have derived it. Okay. So now this was radius of gyration. There is another term from which they can ask question is slenderness ratio. What is slenderness ratio? If you see here, we got our buckling stress. What we got our buckling stress? It was pi square E, then I minimum by L effective square, right, into what? Area. And this was what? This was R minimum square, right? So this becomes pi square E R minimum square divided by L effective square, right? Now I can bring this R minimum down, right, like this, and I can write down this as L effective by R minimum and then whole square. This L effective by R minimum is known as what? The slenderness ratio, and this is pi square E by your lambda square, where lambda is the slenderness ratio. Slenderness ratio is what? Is the ratio of the effective length. It's the ratio of what? The effective length and the minimum radius of gyration of a particular compression member. Slenderness ratio. Yes, slenderness ratio. Yes, easy. Suppose they can ask a question like this. Suppose they ask a question like this. A plate of width 40 mm and thickness suppose 16 mm has a effective length of your 630 mm. Find slenderness ratio. Find what? Slenderness ratio. Okay, very easy question. Yes. See here, effective length is given. If they don't give the effective length, they give the length and the support conditions, then also you can find out effective length, right? So slenderness ratio will be what? Very easy. It is nothing but what? It is L effective by R minimum. Yes. So if you see the solution, it is what? It is L effective by R minimum. And L effective is anyhow given what? 630. And what is R minimum for a plate? We have seen T by root 12. And this is T. So I can say what? T. T is what? 16 by root 12. So this is the slenderness ratio. Again, one more question can be asked like this. Okay, very easy. But if you don't know the things, then obviously they are very tough, right? So getting slenderness ratio of 136.4, right? We're getting a slenderness ratio of what? 136.4. It's a ratio, so no units. Okay. It's a ratio, so no units. Huh? And make sure that in examination, suppose they would have given this as, 0.63 meter also they could have given, right? They have given this as 0.63 meter, right? Right? So make sure that you put in same units. Both should be in same units. mm. It's a ratio. So both has to be in what? Same units. Otherwise you will commit mistake. Okay. The next type of question they ask a lot in the examination is comparing. Okay. Comparing. See, somebody is writing, vulgar comments. Okay, whatever is your name, if you can write your name, then it is better. And please don't waste your time. Okay, I am not doing the activity which you are writing there. I am just teaching from the last 1 hour, and students are studying, and many of the lecture students are studying. Okay, So whatever that person is writing, it doesn't affect me or other students. They are seriously studying. They will be clearing the examination. If you have some personal enmity with me, it doesn't matter. Okay. So I'll suggest whatever your name is, you don't have a name also. So please study. Don't waste your time, because writing such comments is not going to affect me also, or neither the sincere students. Okay. And I'll request other students also not to focus on such kind of people. And I request if someone is there to block, they can block this person. Or if it doesn't block, doesn't matter, because the only thing is that they will come and write such vulgar comments. Doesn't matter. Okay, if you are having some issues, you can visit some doctor. They will get you treated. But don't do this in the class. It is disturbing and it is not a place to write such languages. Okay. Let us solve question. Let us solve a question. Okay. So what I told, in the examination, they will ask lot of questions on comparing. What? Comparing. Okay. What type of questions you see? Suppose I tell that we have a square column. Okay. We have a square column and we have a circular column. We have a square column and we have a circular column. Okay. We have a square column and we have a circular column, right? And then the length of this column is, suppose, 3 meter, and the length of this column is, suppose, 4 meter. Yes. And this column is both ends fixed. What is it? This is both end fixed. Yes. And here one end fixed. One end fixed, other pinned. Okay. One end fixed and other is pinned. Okay. Then it is written that both have, it's a square one and it is a circular one. It's a square one, it's a circular one. And both have same area. Both have same area and material. Both are same area and material. Same material means same E, na? Yes. Same material means same E. So what is asked? The ratio of buckling load of square and the buckling load of column. So this is very commonly asked. This kind of questions are very common in GATE, where they ask you ratio of things. Okay. They ask you what? Ratio of things. Yes. They ask what? Ratio of things. So how to solve? Very easy actually. Very easy. So what I will do is that, you see, the buckling load of square, square, and then the buckling load of column. The buckling load of column, right? So this is pi square E, then I of the square section divided by effective length square divided by pi square E, then I of the, sorry, this is circular, na? What I wrote there? Oh, sorry, circular. Sorry. Okay, circular. Yes. So this is circular divided by what? L effective square of the circle. Now see how to solve. Now first, same material means pi square will get cancelled, E will get cancelled. Very good. Now if you see the square one is what? Both ends are fixed. Both ends fixed means what? Your L effective will be what? L by 2. If this is L by 2, so what will happen? This will become L square, LS square, and then by 2, so become 4, right? You see, I can say LS by 4 means length of the square column divided by 2. So then 4, right? Now this is what? One end is fixed, other is pinned. So what will happen? Here L effective will be what? It will be LC by root 2, right? Means length of the circle by your root 2. So this becomes what? Your length of the circle square, then root 2 square is 2. So if you solve this again, you see this 2 and this will get cancelled. I get a 2. So it is 2, you see, 2 IS by IC, and then I can say LS square LC square, right? Because this LC square will go up. IS by IC, LC square by LS square. Now how to find out this IS and IC? Very easy, you see. IS is what? It's the square column. Suppose I take this as side length as A and this as A. So here BD cube by 12 and DB cube by 12 will be same. So I can take BD cube by 12. So B, D is also A. So by 12. So this becomes what? A to the 4 by A to the power 4 divided by 12. Now for the circle it will be what? It will be pi by 64. I can say D to the power 4. Very good. Okay, very nice. But the thing is that I don't have any relationship between A and D. How to find out? The information given is what? Area is same. So pi by 4 into D square is equal to what? A square. This information is given, right? So from here, can I tell that D is equal to how much A? I can find out, right? This will be 2 by root pi, right? So I can say this will be 2 divided by root pi. 2 divided by root pi. It is 1 point, you see D is 1.128 A na. You see from here I got this now, you see. D is equal to 1.128 A, right? Yes. Yes, I am getting this. So what will be D to the power 4? D to the power 4 I can write down as, I can take, 2 over 4. It is 1.62 approximately, right? 1.62 A to the power 4, right? 1.62 A to the power 4. Very nice. So when I take here ratio, you see, when I take here ratio, IS by IC, IS is what? IS we have got is A to the power 4. A to the power 4 by this. So sorry. So here A to the power 4 by 12, and then I will write down here, less space is there. I need little more space, so I will just add one slide here. So your IS by IC is equal to your A to the power 4 divided by 12, and IC is pi by 64 D to the power 4. So this is equal to A to the power 4, I can write down A to the power 4, and then 64 will go up. So 64 by 12 pi. What is D to the power 4 we got? D to the power 4 we have got is, you see, 1.62 A to the power 4. So it is 1.62 A to the power 4. So A to the power 4, A to the power 4 get cancelled. So how much we get? 64 divided by 12 divided by pi. 64 divided by 12 64 divided by 12 divided by pi, further divided by 1.62. I am getting 1.048. I am getting how much? 1.048. Okay. I am getting what? 1.048. Yes. So this is the ratio I am getting. So now I can just put here, right? I'll just put here very easy, 2 into 1.048. What is the length of the circular column? The length of circular column is 4 meter, and that is 3 meter. So it is what? I can say your 4 square by 3 square. Very easy. So how much I am getting this value? Tell me. It is 16 divided by 9 into 1.048 into 2. I am getting a value of 3.73. The ratio is what? 3.73. Yes. So in the examination, many times what they do is they ask you such kind of ratios. Okay. So in ratios, lot of things get cancelled, right? So LS square, LC square is 4 square. So 16 divided by 9, and that we have got is IS by IC, right? IS by IC we got now. IS by IC is 1.048, and then that 2. Yes, 3.73 approximately. So you see, such kind of questions they will ask in the examination, comparing what? The buckling load. Okay. So any other question they give, you can easily find out. Okay. This will be a typical 2-mark question. If they ask such a question, it will be a typical 2-mark question. They will ask you to compare the buckling load. Okay. So you should be knowing how to find out effective length. I have already taught, right? You should be knowing how to find out what? I, that also I have already taught you. And then some common sense, which should prevail in the examination. The other type of question they can ask is like this, you see. What they will do, that there is a column like this. There is a column like this. Suppose it's a fixed column. Suppose it's a fixed column. Okay. Suppose it's a fixed column and the length is L. Okay. And this fixed column has a buckling load of 800 kilonewton. Or suppose, let me take it something else. Suppose 900 kilonewton. It has a buckling load of how much? 900 kilonewton. Very good. It has a buckling load of 900 kilonewton. Now what they are telling is that suppose in the same column I introduce a pinned, or I pin it at the mid depth or mid height. Means what? I pin it like this at the mid height. So if I pin it, what will happen? How the buckling load will change? That is the question. Okay. If I pin it at the mid height, what will be the effect of this? Let us understand this, and how to solve this kind of questions we should know. So first of all, when I pin it at the mid height, so actually it becomes 2 columns, right? So actually it becomes 2 columns. How? You see, it becomes 2 columns. 2 columns of length how much? L by 2 only. Yes. So it becomes 2 columns. And now I have to find out the buckling load of any one of the columns, right? I have to find out the buckling load of any one of the columns. If I find out the buckling load of any one of the columns, that will do, because both are identical, right? One is fixed, one is pinned, right? Very good. So what I will do, I will take, and suppose they're asking you what is the buckling load of this. So how to find? Very easy, you see. What I will do, I will take this as the buckling load 1. I will take this as the buckling load 1. Now see here, effective length will be how much? Effective length will be length by 2, na? It will be length by 2, because both ends are fixed. So both ends are fixed means what? Length divided by 2. Yes, so I can say here what? L by 2. So for the P1, can I say P1 will be equal to pi square EI by L by 2 square. So I can say L square and then 4. Very good. Now if you see this column, if you see this column, for this column, yes, for this column, it is one end is fixed and other one is what? Pinned, right? If you see the top one or bottom one, they are both same actually, same conditions, right? So identical 2 columns. So either this or this, any one fails, it is failure, okay? So fixed and pinned. So in this case, what is the effective length? The effective length will be equal to length by root 2, right? It will be what? Length by root 2. But here length is how much? Here length is L by 2, na? Yes or no? Here length was L only. But here length of each column is what? L by 2, because we have pinned at the mid. So what will happen? This will become L by 2 root 2. Understood why it became L by 2 root 2? It is length by 2, both end fixed, and length is L. Very good. Here it is length by root 2 and length is equally L by 2. Yes. So when I find out the P2 here, for this one, so what will happen? It will be pi square EI divided by L effective square. So L square, and then what? 2 root 2 square is what? 8. 2 root 2 square is what? 8. Yes. Now when I take P1 by P2, how much I am getting? P1 by P2 I am getting how much? 1 by 2. Because when you take ratio, pi square will get cancelled. Both are same material. So E will get cancelled. See, cross section is not changing. Whatever is the cross section, suppose circular or square or rectangular or I section, T section, nothing is changing. Only we are pinned at the mid. So what happens? The cross section is not changing. Cross section not changing means I will also not change. And L is it is not changing. What is changing? Only this 4 and 8. So P1 by P2 is equal to 1 by 2. Yes. And then I can say, what will be P2? What will be P2? P1 is 900. So P2 will be how much? Your 1800. So the buckling load for when you are pinned here, the buckling load changes to how much? 1800 kilonewton. Right? So 1800 for this, 1800 for this. The two different columns. But don't add to 3600. So when it asked buckling load means you are finding for any one of the columns. Any one column fails means it has failed. Understood? So this kind of questions also they can ask you in the GATE examination. Another question will solve this. You will solve. Here what I will do. Here one end is pinned actually. Yes. And other end was fixed. Other end was fixed. Okay. One end is pinned, another one is fixed. And buckling load for this is suppose 600 kilonewton. Very good. Now what happened? Now I will pin it at the mid depth. Now if I pin it at the mid depth, then what will be the new buckling load for this column? Please find out. If this is L by 2 and this is also L by 2. Okay. Sorry. So, sorry. Having little cough. Okay. So here find out the buckling load. This you try first, then I will solve. I'll give you 2-3 minutes. First you try and then I will solve for you. First you try. Here only one thing I will tell you. See, these are two different columns now. You see, because this is pinned. This is pinned, this is pinned. Right? And this is what? Fixed. Yes. So here these two columns are not same columns. They are two different columns. In the earlier case, they were same column. So what you do, you find out the buckling load for this and buckling load for this. Whichever is higher, take that. Okay. So lower. Which one is lower, you take that. Because lower one will fail first. Na? Okay. First you try, then I will solve for you. Both are pinned, so length only, right? Yes. 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 For this column, L effective will be one end pinned, one end fixed. So it will be length by root 2. That is equal to L by 2 root 2. Right? Understood? It is both end pinned. So L effective will be equal to length only. And length is here L by 2. So L by 2. L effective will be length by L by root 2. So L by 2 root 2. Right? So if I take this as, suppose this is P1. P1 is what? P1 will be pi square EI by L effective square. So L square by 4. This will be 4 pi square EI by L square. If I take this as the second column, so this will be how much? If I take this as the second column, it will be actually equal to pi square EI by again L by 2 whole square. So it is L square and then this is 4. So you see this is 600. So this also will be 600, right? This also will be 600, right? Now if you take this as the P2, so this will be what? Pi square EI by L square and then 8. That is 4 is 600. 4 pi square EI by L square is 600. And this I am getting how much? This I am getting as 1200 kilonewton. So for this column it is 1200. For this column it is 600. And for this column it is 600. Yes or no? Yes. So now, which one will fail actually out of these two easily? This one will fail now because it's having less buckling load. So this becomes the buckling load of this entire thing. Understood? Because if one fails, it fails, na? Yes or no? If one fails, it fails. Understood this question? So answer won't be 1200. Answer will be 600. Because out of this part and this part, whichever is having the less buckling load, that will fail first. Yes or no? And therefore that I will report as the buckling load. Because suppose you are loading it. Initially the load applied was 200. So nothing will fail. 300, nothing will fail. 400, nothing will fail. When it becomes 600, then this one will fail. So it failed, right? Understood everyone? So this type of question when they ask you, here both were same. So therefore it was not it didn't matter. So it was easy. But if you have two different columns, then you take the lower buckling load. Yes, very good. So this was about buckling load and the type of questions they will ask you. So I tried to cover all of them. Yes. Let us go to something known as what? The combined axial load and bending in column. Okay. Okay. Oh, sorry. Yeah. Yes. Sorry. It was pinned, na? Sorry. It was L by root 2. It was L by root 2. I missed it. Yes. It's L by root 2 means it is okay. That means you had pointed out the correct thing. Good. So it is 2 pi square, right? It is 2 pi square. It is 4 pi square. That means this is 1200. Yes. This is 1200 kilonewton. And this is what? This is your 2400. Yes. This is 2400. L by root 2. Why? Because it is one end is pinned and this was fixed. I missed it. So therefore it is length by root 2. So L by root 2. So this is 2 pi square. and this is 4 pi square, and this is what? 8 pi square. So again, this one is the minimum only. So the buckling load of this I will take as the buckling load, just the value changed due to my mistake. Understood? Yes? Okay. Next, I told what? The next is combined axial load and bending in columns. Okay. So what is this? Very easy. You see, suppose this is a column. And suppose I am applying a load such that the load is applied at the centroid. Right? It is passing through the longitudinal axis. It's an axial load, it is passing the longitudinal axis. So what will happen? This is known as concentric load. Yes, this is known as what? Concentric load, or I will call this as what? Pure axial load. I will call this as what? Pure axial load. Or I can call this as what? Non-eccentric load. I can call this as what? Non-eccentric load. Yes, or zero eccentricity load. Right? So in this case, there will be only axial load, and due to axial load, there will be what? Normal stress or axial stress, and that will be simply what? The load P divided by what? Area. So only we'll get what? We can say axial normal stress I will get. I'll get what? Axial normal stress. Very easy, very good, nice. But if suppose there is some eccentricity, yes, so if we have a column like this, yes, if we have a column like this, this is the longitudinal axis, and the load is applied at a particular eccentricity, suppose E eccentricity. So what will happen? In this case, what will happen? To see the effect, what I will do? I'll shift the load. So when I shift the load to the longitudinal axis, so whenever we shift load, what happens? There is a moment also, right? One second. So in this case, there will be a moment also. So let me shift the load. So there will be a axial load, and then there will be a bending moment also. M and P, right? And this M will be what? P into E. Yes. So here two things will come into picture. So therefore what I have written? Combined axial load and bending. So two things will happen. One in what? There is due to P, I will get normal stress. How much? It will be P by A. Right? Now due to your bending moment, we get what? Bending stress. And what was the bending stress equation? It was My by I, right? And then I can say, if I take the maximum value of bending stress, it was equal to what? M by Z. Yes, we have seen this, right? M by Z. Yes. So due to axial load, I will get the normal axial stress, and due to bending moment, I will get bending normal stress. Both are normal stresses only, but there is a difference. What is the difference? Let us see. Let us see what is the difference. So now suppose the cross section is rectangular. It can be anything. I am just drawing a rectangular. I am taking reference of rectangular. Then what will happen here? You see, You see, this is the cross section. Suppose it's rectangular column. Can be circular also. I am taking rectangular. Now, due to P is the compressive load, and this stress which I will get, it will be what? Compressive, entirely compressive. So P by A, I will get a uniform stress like this. I'll get a uniform stress like this. This P by A, it will be entirely compressive, and I'll get what? P by A. This stress I will get what? P by A. And suppose compressive I am taking as positive. Suppose I am taking as positive sign. Yes. So due to P, I am getting this normal stress P by A. Now due to bending moment M is equal to P into E. What will happen? I'll get bending stress, and bending stress is what? It is linear distribution, right? 1 second, I'm getting little cough. Due to P into E, I will get what? I will get a linear distribution. I'll get what? Linear distribution, right? And we have already seen that one side it will be compressive and one side it will be what? Tensile, and maximum will be at the extreme fibers, right? So this will be M by Z, right? And here it is plus, but here it will be tensile. Or it can be opposite also, but one side it will be plus, one side it will be tensile. So if I take the net effect and the net stress distribution, I'll get something like this, right? See, either I can get like this, you see, either I will get a distribution something like this, you see. Yes. And this will be what? P by A plus M by Z, right? P by A plus M by Z, right? P by A plus M by Z. And here I will get what? P by A minus M by Z, right? P by A minus M by Z. Now, if this P by A is greater than M by Z, then I'll get positive here, and this anyhow will be positive because this is positive and this is positive. And if suppose P by A is greater than M by Z, P by A is greater than M by Z, then I'll get what? Entirely positive here. But there is a chance that I might get negative also, right? There is a chance here that I might get negative also. How? Something like this, you see. I might get something like this distribution also. Yes, I might get negative, or I can say it might get tension. This is P by A. This will remain a positive only, P by A plus M by Z. That is not a problem. But here what will happen? This P by A minus M by Z. Yes. And if I am saying that your P by A is less than M by Z, then I might get what? Tension here, right? And if P by A is greater than M by Z, then I will get compression here. Yes, understood this? So I can say that there is a possibility of tension here if P by A is less than M by Z. Yes. So if I say to avoid tension, if I say to avoid tension means that no negative. That means what? P by A should be greater than equal to M by Z, na? Yes, you see. If P by A is greater, then I'll get compressive. If it is equal to, then I'll get 0 here actually, right? If it is equal, then I get a 0 here. If it is less, then there is a problem, right? Yes. So I can say here that to avoid tension, P by A should be greater than M by Z. Yes. And what is M here? M is P into E, right? So E gets cancelled, or I can say that eccentricity should be less than Z upon A. Eccentricity should be less than what? Z upon A, right? So yes, eccentricity can be there, but if E is less than Z by A, yes, this E, you see, there is eccentricity of loading. Eccentric loading is fine, right? But if I say that this E is less than Z by A, then what will happen? Then I will say that I have avoided tension in the column, right? So this is the condition for what? To avoid tension in column. So to avoid tension in column, the eccentricity should be what? Less than Z by A. Yes. And what is Z? Z is your section modulus. What is Z? Z is your section modulus. We have already learnt about section modulus in bending stress chapter. And A is your cross sectional area. Yes. So this leads us to the concept of what? Kern zone. This leads us to the concept of what? Kern zone. What is Kern zone? I'll tell you. Suppose I'll take a circular area. I'll take a circular area, right? This is the center. Yes, this is the center. Yes. And suppose I am drawing the both the axes. Let me draw both the axes. Yes. Now see, to avoid tension in this cross section, E has to be less than equal to what? Z by A. Now what is Z for a circular section? We know pi by 32 d cube, right? Or Z is what? I by y max. We have seen this, right? Section modulus, right? So I for a circular section is pi by 64 d to the power 4 divided by y max is how much? D by 2, right? Y max means from the neutral axis maximum distance. It is d by 2. So this is what? Pi by 32 d cube. What is area? Pi by 4 d square. Pi get cancelled, this get cancelled, get a d, and this is what? D by 8. Yes. That means when the eccentricity is less than equal to d by 8, yes, then there will be no tension developed in the column, right? So eccentricity d by 8 means this is d by 2, so d by 8, so 1/4 of that somewhere here, right? So if eccentricity is this much, is within this or within this, okay, or within this or within this, that means what? There will be no tension. So this thing which you are getting, this zone which you are getting, right? So in this entire zone, yes, in this entire zone, what happened? In this entire zone, your eccentricity is what? Less than d by 8. Yes, in this entire zone, your eccentricity is what? Less than d by 8. Yes, this is d by 8 or less than equal to d by 8. So this is d by 8. This is d by 8. Yes, this is d by 8. This is d by 8. Anything you see, d by 8. And this point will have obviously less than d by 8. And this zone is known as what? 𝐿 zone. Yes. So that means how I define the 𝐿 zone? 𝐿 zone is a part of the cross section of column, is the part of the cross section of column, is the part of cross section of column such that if axial load is applied in this zone, no tension will develop, anywhere, not only in 𝐿 zone, anywhere in column. So in the entire column cross section, what will happen? There will be only compression. Yes. So this is the 𝐿 zone. So for a circular section, yes, you have to remember this. Anyhow, I have derived it. So for a circular section, the 𝐿 zone is what? The 𝐿 zone has a radius of how much? This is the 𝐿 zone, right? You see, this is the 𝐿 zone for a circular section, right? This is the 𝐿 zone, right? So this 𝐿 zone, okay, for a circular section has a radius of how much? 𝐿 zone has the radius of your d by 8. And what is the diameter of the 𝐿 zone? What is the diameter of the 𝐿 zone? The diameter of the 𝐿 zone is d by 4, right? You see, the eccentricity is d by 8. So this is d by 8. So this entire one will be how much? This will be d by 4. So d by 8 and then d by 8. Yes. So the diameter is what? D by 4. And also, if I say the eccentricity of load, the eccentricity of load for 𝐿 zone is, that is also d by 8 only, right? Eccentricity of the maximum eccentricity, not the minimum. The maximum eccentricity of load will be what? It is d by 8 only. Because if you see, when we found out, it is E is less than equal to d by 8, right? It is less than equal to d by 8. So that is d by 8 is what? The maximum eccentricity. And all these things can be asked in numericals also, and directly they can ask you questions also. Yes, and the 𝐿 zone is also circular in shape. Now, if we take a hollow circular section, if I take a hollow circular section, hollow circular section means what? This is nothing is there, hollow. Suppose this hollow, this internal, suppose I am taking small d, suppose I am taking this as small d, and this external, suppose I am taking as capital D. So in this case, if I want to find out the 𝐿, so what will be E? E will be less than equal to Z upon A. Now, if I want to find out the Z of this hollow thing, Z will be I by Y max. Now, what is I? I for a hollow one will be what? Pi by 64 capital D to the power 4 minus small d to the power 4, right? Yes. Divided by Y max. Y max is what? Y max is here is D by 2 only. If you see, Y max means what? From the center, maximum one will be capital D by 2, right? So this will be capital D by 2. So this gives me, you see, pi by 64. Yes. Then I can say D pi by 32 actually. Capital D to the power 4 minus small d to the power 4. I can write this as d square minus small d square, and then this d square plus small d square, and then further divide by what? 8. But d. Yes, this I get as what? Your Z. Yes. So Z is what? Z is pi by 32 d square minus d square, then d square plus d square divided by capital D. Now what is area of this? Area of this hollow one is what? Pi by 4 capital D square minus small d square. This is the area. Then what happens, you see? These two get cancelled, right? Pi get cancelled. This get cancelled. I get a 8 here, right? And I get what? The eccentricity, how much I am getting? The eccentricity will be less than equal to capital D square plus small d square divided by 8 capital D. So this is the eccentricity of what? This is the eccentricity of the 𝐿 for the hollow circular section, right? And suppose if you put, for making it solid, if you put small d as 0, it will be d square by 8d, which will become 8d by 8 as in the solid one, right? Yes. So if they ask you a question like this, suppose they are giving you that we have a hollow circular section. Yes, we have a hollow circular section. Yes. And the external diameter is given as 100 mm and the internal diameter is given as your 60 mm. Yes. And we are asked that what is the diameter of 𝐿? What is the diameter of 𝐿? Yes. So that is, first of all, what we get is the eccentricity, right? You see, what we get is the eccentricity. Yes. So diameter will be twice of eccentricity, right? Yes. You see here. You see here. What we have got, sorry. You see, like the solid one, what we got? Eccentricity as d by 8. Diameter is twice of that, right? Because eccentricity will be from center, right? So it is from center. So whatever I get eccentricity, diameter will be twice of it. So first of all, let us find out the maximum eccentricity here. So eccentricity will be how much? Maximum eccentricity will be d square plus small d square divided by 8 capital D, not small d, remember. So 100 square plus 60 square divided by 8 into 100. So how much you are getting this? Find out. What is the answer we are getting here? So 100 square plus 60 square divided by 8 divided by 100. Some calculation mistake. 17 we are getting, right? Yes. We are getting how much? 17 mm. Right? This is the eccentricity. So what is the diameter of the 𝐿? It will be 2 times the eccentricity. That is equal to 34 mm. Right? That is how much? 34 mm. Understood? Very easy question. But you need to remember the formula. If you can't remember the formula, you can always find out. Okay, you can always find out the way I have found out, right? I've explained how to find out also. Now, if this same question, if it was solid one, if it was solid, okay, solid circular section, if it was solid circular section, right, a solid circular section, and suppose it was only one diameter, suppose D was 100 mm only, right? So in this case, the diameter of cone would have been how much? Only D by 4. Now I have already found out, because eccentricity will be D by 8. So only D by 4, that is how much? It will be 25 mm, right? It will be what? 25 mm. Yes. Diameter of the cone will be 25 mm, right? D by 4. Because eccentricity will be D by 8. So eccentricity D by 8 means diameter of the cone will be twice of that, right? Diameter of the cone will be twice of that. Yes. Understood? Yes. So this kind of very simple question they can ask you. Numericals also, even they can ask you expression also, right? They will give you 4 options and they will ask you which one is the right expression for finding what? The eccentricity. But remember carefully. Yes. Remember carefully. Eccentricity and the radius of the cone will be same, right? Yes. Eccentricity and radius of the cone will be same. Diameter will be 2 times the eccentricity, right? Diameter will be 2 times the eccentricity, obviously, right? And if you forget the formula, always remember you can derive it where? How? Z by A. Okay, this is the core formula which we derived, right? Initially I derived this formula. Yes, Z by A. And you know how to find out Z, you know how to find out A. Let us see for a rectangular cross section, right? Let us see for a rectangular cross section what happens. Yes, let us see for a rectangular cross section what happens. Yes, for rectangular cross section, you see there are 2 dimensions, right? And there can be bending about both axes, right? The rectangular cross section, let me draw it a little bigger. Okay, so if I'm finding about, see, if I'm finding about x-axis axis, so this is the center. If I'm finding about x-axis axis, then about x-axis axis, E should be less than equal to what? Z by A. Now about x-axis, the Z will be BD square by 6, right? It's rectangle. So it will be BD square by 6. And what is area? Area will be B into D. So B into D. So what happens? B get cancelled, D get cancelled. I get what? D by 6. Yes. So I get eccentricity of what? I get eccentricity of D by 6. So this side D, 1 second. Bending about x-axis axis. So when I'm taking bending about x-axis axis, yes, I will take the I about x-axis axis. Yes. So E should be less than equal to your Z-axis by A. Yes. So Z-axis will be BD square by 6 only, and then BD, that is equal to D by 6 only. 1 second, let me just cross check. Correct. So E should be, yes, E should be what? It should be less than D by 6. E should be less than D by 6. Now when I am telling that bending is happening about XX, yes, when I am telling that bending is happening about XX, that means the load will be on y-axis, na? Yes or no? Or eccentricity will be about y-axis. When the load is acting here, then there will be bending about x-axis, na? If I draw in 3D, yeah, I'll draw in 3D. You see, this is the cross section, okay? And this is what? This is your this x-axis. So when it is x-axis, I am telling that bending is happening about x-axis. So load has to act somewhere here, na? Then there will be what? Bending about x-axis. Yes or no? When the load is acting here or here or here, then bending will happen about this axis. Yes. So therefore, this eccentricity which I have got here is less than equal to D by 6. This is about what? Y axis. So I can say here, this is D by 6 this side. Yes, D by 6 this side, and then D by 6 this side. Yes, D by 6 this side. Now when I'm talking about bending about y axis, so when I'm talking about bending about y axis, then what will happen? When bending is about y axis, then E has to be less than equal to what? Z y by A. And Z y is what? dB square by 6. And dB square by 6 area is BD. This becomes what? You see, DD get cancelled, B by 6. So your eccentricity becomes less than equal to what? B by 6. Now when I am saying that bending is happening about y axis, then the load has to act in x axis, na? Then only what will happen? There will be bending about this axis. Yes or no? When load is acting along x axis, then I can say what? Bending will happen again y axis. So here I can say this side B by 6, yes, and this side B by 6, right? So the Ch zone will be this one, and the Ch zone is actually a rhombus here, right? The Ch zone is actually a rhombus here, you see, something like this. Yes, so this is the Ch zone, right? So it is a rhombus, yes, and I can say that what the diagonal length? So for this Ch zone, yes, so for this Ch zone, yes, of rectangle, I can say of a rectangular cross section, yes, what are the eccentricities? Eccentricities are less than D by 6 if you see along the depth. Yes, this is D by 6 along the depth, right? Eccentricity is D by 6 along the depth, right? Because depth is this one, na? You see, depth is this one, na? And it is B by 6 along the width, right? So this is what? Along depth, yes, and this is less than equal to B by 6 along width, right? And then this is the thing. But if I consider the diagonal length, yes, the Ch zone is like this, you see, we can say a parallelogram also. If the Ch zone is like this, yes, yes, so here we have two diagonals, right? You see this diagonal and this diagonal, right? So see, eccentricities are d by 6 and b by 6. But what is the diagonal length? Diagonal length will be b by 6 and b by 6. That is how much? B by 3, and this is d by 6, d by 6. That is what? Your d by 3, right? So remember this, okay, directly they can ask you. So if I conclude here, all these things can be directly asked in examination, okay? So if I conclude the 𝐿 zone, okay, so how we are getting the eccentricities? The basic equation is what? E is less than equal to Z by A, right? Then for a circular section, the maximum eccentricity we got was d by 8, and this was radius of 𝐿 zone, right? This was radius of 𝐿 zone, and the diameter of 𝐿 zone was d by 4. Diameter of 𝐿 zone was your d by 4, right? And then we saw that for a hollow circular, okay, then we saw that for hollow circular, right, the eccentricity is d square, the outer one, then inner one square divided by 8d, and this is also the radius of 𝐿 zone. This is also the radius of 𝐿 zone. That means 𝐿 zone is circular here, right? Right? But the diameter of 𝐿 zone, I can say, diameter of 𝐿 zone will be just twice of the eccentricity. Twice of the eccentricity. This is for hollow circular. This is for hollow circular we saw. And this is for circular. And then we saw for a rectangular, and rectangular will hold for square also, right? It's really parallelogram I will get, right? And in this, the 𝐿 zone, eccentricities are what? B by 6 and D by 6. Eccentricities are B by 6 and D by 6. But what are the diagonal length? The diagonal length are B by 3 and D by 3. So read the question very carefully in the examination, what they are asking. Okay, read the question carefully. Students, they jump into the examination whenever there's a question, they start jumping. Don't do jump. Okay, read the question. Rectangle, if they ask you eccentricity, b by 6, d by 6. If they ask you diagonal length, b by 3, d by 3. Same for hollow circular and circular. Yes. Then a small topic, I will take 15 minutes extra and complete that. That is combined bending and torsion. Very easy topic actually. So we'll complete in 10 minutes. So combined bending and torsion, very easy. And if they ask question, then you can easily answer. So suppose this is a shaft. This is a shaft, okay? This shaft is suppose having a longitudinal axis. This is the longitudinal axis, right? And this is the lateral axis or transverse axis. We have seen in the starting of the course that when there is bending moment about the longitudinal axis, that is what? The twisting moment. And when there is bending about the transverse axis, this is what? Bending moment. So this is the transverse axis and this is the longitudinal axis. And suppose both moments are acting together. The twisting or torsional moment is there and then the bending moment is also there. Both are there. Then what will occur? From this many questions are asked and we should know this. So see, what will happen you see. And suppose the diameter is D for this circular shaft. Now we know that when there is twisting, due to twisting shear stress is there. So shear stress will be how much? Maximum shear stress was how much? 16 T by pi d cube, right? Remember? Yes, this was the maximum shear stress due to torsion, right? We have already studied this due to torsion, we will get this shear stress, right? Yes, you have already seen this, right? With torsion. Now we get the shear stress. Now due to bending, we get what? Bending stress, and it's a normal stress, right? Due to bending moment, we will get bending stress, which is a normal stress, right? And what is the maximum bending stress we'll get? It was m by z, right? Remember, m by z. Remember, this was actually what? Shear stress maximum was T by Zp, and Zp was pi d cube by 16. Remember, and when I do this bending moment, this is m, and what is z for a circular section? Z for a circular section is pi d cube by 32, na? Yes, we have already seen this. See, z for, now only we saw, right? Z for a circular section. When I'm finding 𝐿 zone, you see, when I'm finding 𝐿 zone, you see, it is how much? You see, this is what? D cube, and this is 32. So pi by 32 d cube. Okay. So this is what? Z. Therefore, I taught you first all those bending stresses and all. Those who are attending regularly, they will be having some benefit. So this is what? This I am getting as what? The maximum normal stress, and this is the shear stress I am getting, right? This is the shear stress I am getting, right? Yes. This is not a rectangular section, it's circular section. Okay, soft circular section. So in the examination, what they will ask you, I will tell you. They will ask you, what is the ratio of your normal stress and shear stress? What is the ratio of normal stress and shear stress here? Very easy, na? See, the ratio of normal stress and shear stress will be what? It is your sigma by tau. So what is your sigma? We got that as 32 m by pi d cube. And what is the shear stress we got? 16 t by pi d cube, right? So pi d cube get cancelled, and this is 2. So I get what? 2m upon t. I get what? 2m upon t. So this is the ratio of what? The ratio of the normal stress and shear stress. Such kind of very straightforward questions are asked. But if you know the things, then only straightforward, otherwise it is very difficult, right? Ratio of what? Normal stress and shear stress. Now also we have studied in the chapter of Morse circle for stress and strain. Suppose this is the stress element, and then what I got? I got only one normal stress. Yes. So that normal stress is what? Suppose your sigma x. Okay. I got only one normal stress. Sigma x is equal to how much? I got 32m by pi d cube, right? And then I got only sigma x. There is no sigma y here because only one normal stress is there. And I got the shear stress how much? I got the shear stress how much? That is 16t by pi d cube. And suppose I take that as tau xy. Yes, because I got only one shear stress. So that is the one shear stress I will get. And then I got this normal stress. Only one normal stress, I take that as sigma x. We can take sigma y also, no problem. I have taken sigma x. Okay. If I take sigma x, then sigma y is 0. If I take sigma y, then sigma x is 0. Okay. Now in this case, yes, I can draw the Morse circle, right? For this stress data, I can find out the Morse circle, right? And what will be the center of that Morse circle? The center C will be equal to what? It was sigma x plus sigma y by 2. That will be how much? Sigma y is anyhow 0. So it will be nothing but 16m by pi d cube, right? 16m by pi d cube. And what is the radius? The radius will be equal to, you see, radius was what? It was root under sigma x minus sigma y by 2 whole square plus tau xy whole square. Anyhow sigma x is sigma y is 0. So what I will do? Sigma x by 2 will be what? 16m by pi d cube whole square, and then tau xy is 16t by pi d cube and then whole square. Yes. So now you see what happened. Is I can take 16 by pi d cube square common in both, you see. 16 by pi d cube square common. When I take it out of the bracket, it will become 16 by pi d cube. I'll take 16 by pi d cube square common. So when I take it out, I'll get what? 16 by pi d cube. So this radius becomes what? This radius becomes equal to, you see, I take out this 16 by pi d cube common. So this becomes what? Root under only m square plus t square. So I got the radius of the Mohr circle. I got what? I got the center of the Mohr circle, 16m by pi d cube. So if somebody asks me to find out the principal stresses, I can find out, right? What was the major principal stress? The major principal stress what? Center plus r. So you see, it is center was what? 16m by pi d cube, and then r was what? 16 by pi d cube. Yes, and then root under m square plus t square. Or I can say what? I can take 16 by pi d cube common, and then I can write down what? M plus root under m square plus t square. This is what? This is the major principal stress. And minor principal stress is what? It is C minus R, that is equal to, you see, only it will change the sign, right? So I'll write down 16 by pi d cube, then I'll write down m minus root under m square plus t square. Very easy equations, right? So this manner we can find out the principal stresses. Yes, the principal stresses. And if I want to find out the maximum shear stress, that was actually equal to radius, na? So this becomes what? The maximum shear stress, right? This becomes the maximum shear stress. Yes. So they can ask you very simple questions like this. You see, they might ask you a question like this, that a circular shaft has a diameter of 150 mm and it is subjected to a bending moment of 25 kilonewton meter. Yes, and a torsional moment of 10 kilonewton meter. Yes, and they can ask you, find out the principal stresses. They can ask you what? Find out the principal stresses. Yes. So if this is the case, very easy we can find out, right? First you find out the center of the Mohr circle, right? First you find out what? The center of the Mohr circle. What's the center of the Mohr circle? The center of the Mohr circle is 16 m by pi d cube. We have derived it. So 16 m. Now convert everything into Newton mm. Convert everything Newton mm. So 16 m 25 into 10 to the power 6 divided by pi d cube. D is how much? 150 cube. So how much you are getting this center? Tell me. How much you are getting center? Tell me. The center will be 16 into 25 to 10 to the power 6 divided by pi, further divided by 150 cube. It is 37.73. Very good. 37.73 MPa. I am not writing. It will be MPa only. Let me write also MPa. Then what is the radius? Radius will be 16 by pi d cube. Okay. Then m plus root under m square plus t square, right? So what we will do, we will put this as 16 by pi d cube, and then you see in everything there is 10 to the power 6 only, right? 10 to the power 6 I will take common actually, and then it will be uh, 25 plus, right, root under 25 square plus 10 square. Since everything 10 to the power 6 will be common, so I am just taking the 10 to the power 6 common. So 25 square plus 10 square, I'll take the square root of that, plus 25 into 10 to the power 6 into 16 divided by pi, further divided by 150 cube. I'm getting 78.36. I'm getting the radius as what? 78.36 Newton per mm square. Right? So we got the center, we got the radius. You see, this can be a 2-mark question, ladies and gentlemen. This can be a 2-mark question. This can be an MSQ also in your examination. Okay? This can be an MSQ also. So please be very serious. Whatever I am teaching with an mindset that which are the most probable things for your examination. So all these things are very serious stuff. But I am not going into any hurry. I am not having some predeterminate equations. I am all deriving it so that you are benefited. So what is the sigma 1? Your sigma 1 is how much? What is sigma 1? Very easy, C plus R. And sigma 2 is C minus R. Very good. Easy. C plus R. So 37.73 plus 78.36. That is 116.1 approximately, right? 116.1 approximately. That is the major principal stress. And minor principal stress is, I'll subtract that. So 37.73 minus 78.36. I am getting a negative value, tensile value, right? So I can say minus 40.63 MPa. That means this is compressive, okay? So whenever I get a positive, I take that, sorry, ulta. I take that as, here I take as tension, right? Here I take as tensile, remember? And here I take as compressive. I have explained in more circle. Tensile I take positive and compressive I take negative, right? And then suppose if they ask you maximum shear stress, the maximum shear stress is anyhow what? It is R is equal to this one. This will be the maximum shear stress. Easy, very easy, right? Very easy. One last thing I will tell you, that is the concept of your equivalent bending moment and equivalent torsional moment. Last thing we'll study is equivalent bending moment See, it is taking little more time because actually I am writing all the things. If you see, I write all the things. I don't like that PPT thing, you know, everything is written and just tell that this formula, this formula, this formula, this formula. I don't like that. I like it when I write everything on the board. So I am little old fashioned teacher. I am not little modern. I am little old traditional teacher, very old teacher. So I like writing the things only on the board. So equations, anything I write, I like it to write. So it is taking little more time, but I feel that is more effective. So what is this effective bending moment? The equivalent bending moment, ME. What is this ME? Okay. This ME is very easy, you see. Suppose we have a shaft. Okay. We have a shaft. And suppose we have two shafts, same shaft. And suppose in this I am applying only ME. Right? Right? And here I am applying torsional moment T and bending moment M. Okay. Now, what is the maximum normal stress developed here, or sigma 1 suppose, the major principal stress. The major principal stress, how much you will develop? The equation was what? You see, major principal stress. The equation was this one, no? You see, this was the equation. In this equation, we'll put ME and T is equal to 0 because no torsional moment is acting, right? So it will be what? It will be equal to, you see, it will be equal to 16 by pi d cube. I'll put ME plus root under ME square because T, no torsion is there. So what happens? This becomes ME plus ME, that is equal to 32 ME, right? Pi by pi d cube. And what is the sigma 1 here? The sigma 1 here is 16 by pi d cube m plus root under m square plus t square, because both m and t are acting, right? So what is this equivalent bending moment? This equivalent bending moment is the bending moment such that the major principal stress, and major principal stress is the maximum normal stress, they both are same. So either you apply M and T or you apply ME, the major principal stresses are same. So if the major principal stresses are same, if I equate them, so what will happen? In this case, I am getting 32 ME by pi d cube. In that case, I am getting how much? 16 by pi d cube m plus root under m square plus t square. So what happened? You see, this pi d cube cancel, this becomes 2 and this becomes 1. And what is equivalent bending moment? The equivalent bending moment is m plus root under m square plus t square divided by 2. That means if you apply a bending moment equal to this value, you will get the same major principal stress as you get for the combined effect of what? Your bending moment and a torsion. Yes. So I can write down the definition like this, that equivalent bending moment, yes, equivalent bending moment produces what? Produces same major principal stress, produces what? Same major principal stress. And by the way, the major principal stress was what? It is the maximum normal stress. It is what? It is the maximum normal stress. Yes. So this equivalent bending moment produces same major principal stress or maximum normal stress as produced by combined effect of bending moment and torsion. And torsion moment and torsional moment, right? This is T and this is M and this is what? ME. Okay, so very basic question they can ask you, like suppose they give that, you know, M is equal to 50 kilonewton meter, right? And suppose T is equal to 20 kilonewton meter, and they will ask you, you know, find out the equivalent bending moment. Now, if you know the formula, it's very easy, but I derived it so that, you know, you get an understanding of things. It is simply M plus root under m square plus t square divided by 2. I have derived it. Very easy. So how much you are getting this? It is actually 50 plus root under 50 square plus 20 square divided by 2. So 50 square plus 20 square plus 50 divided by 2. Wait. 50 square plus 20 square root of this plus 50 divided by 2. 51.926, or we can write down 51.93 kilonewton meter. So if you apply these two, or you apply this one, you will get the same maximum principal stress. You will get what? Same maximum principal stress. Then there is the concept of your equivalent torsional moment. What is this equivalent torsional moment? The equivalent torsional moment is such that I'll call that as TE. So if only TE is applied, what is the maximum shear stress? The maximum shear stress is radius, na? And radius was how much? Radius formula was how much? You see, radius formula was this one. You see, this is the formula. In this, only T is applied, so M is 0. So 16 by pi d cube, and then I can say root under m square plus t square, so m is 0, so only t, right? So only t is applied. This is the maximum shear stress, and due to the combined effect, okay, due to the combined effect, it is how much? 16 by pi d cube and then root under m square plus t square. Yes. So equivalent torsional moment is that torsional moment such that when applied alone, it produces the same maximum shear stress as produced by the combined effect of bending moment and torsion. Yes. So equivalent bending moment was what? Equivalent bending moment was the bending moment such that, yes, it was the bending moment such that the major principal stress was same, okay, as produced by what? Combined effect of bending moment and torsion, right? But your equivalent torsional moment is that torsional moment when applied alone, it produces what? Same maximum shear stress. So from here, can I say, comparing T is equal to nothing but root under what? M square plus T square. So that means here in this question, if I ask you what is the, here it was equivalent bending moment. If I ask you equivalent torsional moment, what is this? It is nothing but simply M square plus T square. That is equal to how much? Root under 50 square plus 20 square. That is 53.85. 53.85. Yes. So this equivalent thing they can ask you, very easy thing, and they can ask you. So if I summarize it, that when I am taking what? Equivalent bending moment, that is equal to what? M plus root under M square plus T square divided by 2. And how I found out? That the major principal stress due to ME, I equated it to what? Major principal stress due to M and T, right? And then what was the equivalent torsional moment? It was your root under M square plus T square. And how I found out? The maximum shear stress, yes, due to TE is equal to the maximum shear stress due to M and T, combined effect of what? M&T. So this was all about today's lecture. Okay. So I tried to cover all the important things. Okay. It was a little lengthy, but that is worth it. Yes. So that's it. We'll not extend more. Tomorrow we'll study deflections. So what we have studied, actually we have studied a lot of things. We have studied the concept of Euler's buckling load, right? We studied the concept of Euler's buckling load, right? In Euler's buckling load, we studied many things actually. In Euler's buckling load, we understood how to find out effective length with the different complicated language which I mentioned, right? Then we learnt about the radius of gyration also, and I told lot of questions on radius of gyration also can be asked on circular section, on plate, I have explained also. Then we studied about slenderness ratio also. Even they can ask you slenderness ratio, right? Yes. Then they can ask you questions on comparing the buckling load and all. Then we studied about the combined axial load and bending, and in that we studied mostly about what? Kern zone, right? Kern zone, very important topic. In that we saw circular section, yes, rectangular section, yes, and hollow circular section, right? Hollow circular section. Okay. Then we saw the concept of what? Combined bending and torsion. We saw the concept of combined bending and torsion, and I taught you how to torsional moment basically, and I taught you how to find out, right? For this, the major principal stress, minor principal stress, and the maximum shear stress, right? And also we saw in this the concept of what? The equivalent bending moment, and then what? The equivalent torsional moment. What are these concepts? And also what are the values? How to find out the values? I think a lot of things are studied. Tomorrow we'll study your deflection of beams. So I'll try to cover as much as possible in deflection of beams. So thank you very much for your patient hearing. Great.